Thank you so much. And it looks like my headset has died, so I'll be going off of my computer's mic. But let me go back to the problem. And okay. Okay. So back to the problem, we're going to take a random sample of okay, so our job is to find 90% confidence intervals, and there are two forms of a confidence interval. So there are two forms, and I want you all to tell me what are the differences between the two forms for a confidence interval on the mean. Okay, so one form is to calculate x bar plus or minus t of n minus 1 of alpha over 2 times s over root n. And the other one is very similar. Okay, what's the difference between these two forms? So like one of them has a t, one of them has a z. What do those stand for? And another one, in 1 versus 2, there's an S, and in the other one, there's a sigma. What do those things represent? So I have a teaching assistant for today, and she's going to tell us exactly. It's this, one of them's the z-score. So, and the other one is a t-score. Okay, so a t-distribution versus a z-distribution. So one big difference here is going to be this object versus this object. So sigma is the population standard deviation. Whereas S here, this one is the sample. So you have to decide, is your standard deviation calculated, given to you from a population, or does it come from a sample? And if you're given sigma, someone has to tell you what that value is, okay? Whereas if you're using S, that comes from a sample. 90% of the time you're going to use that first form. You're going to have a sample standard deviation. This is most instances, but I should let you know that on your review, there is an instance where you need to use formula 2. So this is most instances. Because it's not very realistic to have a population standard deviation. So most of the time you're given, you would use equation 1 because you calculate everything from a sample. So this one is sample standard deviation. And the key is that the sample is calculated from your sample data. Okay. Then Zach said that there's one other thing. This has a normal distribution, whereas this one comes from a t-distribution. Okay, so now that we've identified that there are two forms, well, we should notice that we have a random sample of n equals 30, and we're told that the mean is 51, that's x bar, and a sample standard deviation. So we're told that this is S, and we're also told that x bar is this piece right here. So we know a whole bunch of information. Let's just play write what you know. So to answer your question, Shelby, S is for sample standard deviation. So yeah. Okay, so I'm just going to write what we know. And in the PowerPoint slides, I call this name the variables. So I know that x bar is 51. I apologize for my poor handwriting. We know that the sample standard deviation, S, is 6. We know N is 30. And we also know that I want a 90% confidence interval. So 90%, that's going to be 1 minus alpha. So alpha is equal to 10%, and alpha over 2 is equal to 5%. So we need to use a t-distribution. And I'd like to point out the t-distribution, it looks a lot like a normal distribution. And there's one thing that I left off. What does a t-distribution have? So that I didn't say. So a t-distribution has degrees of freedom, which I'm just going to call df, and that's n minus 1. So it has 29 degrees of freedom. And what happens is in my t-distribution, I want 90% to be right there. I want 5% right there, and that's alpha over 2. And I want another alpha over 2, which is 5% in that tail. So 1 minus alpha refers to the range between the t-distribution. The alpha over 2 is how much area is in each tail. And the question is, what's this value? Okay, and to answer this question, we need to use a calculator. Okay, and so my question to you is, do you want to use the calculator that's online in your textbook, or do you want to use the calculator or do you want to use R? Okay. By the way, both of them will be available to you on your exam. So you're allowed to access your calculator and your textbook online. You're allowed to use R online. but you're not allowed to use anything else. So let me just stop the share for a second. And let's go to your calculator. Just give me a second.
Professor Chan, can I ask a quick question?
Please.
So is alpha only 10 because it's 90%? Like, so
Yes.
if it was like, then it would be 20?
Say that one more time. If it was what? It would be 20?
So like if it was 80%, like we wanted to find an 80% CI, would then alpha be 20?
Exactly.
Okay, awesome,
And,
thank you.
and one thing that you are really interested even more than alpha is alpha over 2. Okay, so you go to your calculator section here, and what we want is the inverse t distribution. Okay, so it lets us select our confidence level. So we knew that we needed a 90% confidence interval. So you don't even have to figure out what alpha is for this calculator. If you were to use R, or if you were to use a standard statistics textbook, you would need to calculate alpha over 2. But for your textbook doesn't require that. So your degrees of freedom here is going to be 29. You need to figure that out. You need to select your confidence level, and then we'll determine our value of t. And our value of t is going to be this 1.699. Okay, so I'm going to put us back on the iPad. Okay. Okay, and so this is the value we needed from the calculator, this 1.699 right here. So now we know all the information. We know x bar, we know t of 29 degrees of freedom and alpha over 2 times s over root n. So now all we have to do is plug this in. X bar is 51 plus or minus 1.699 times s, and s we have is 6 over root 30. So just give me a quick minute and I'll do this calculation for us. So in your calculator, you should get this number. So the larger number will be 52.8. And your lower number will be 49.1. Okay. And sometimes it's instructive to write this as an interval. So if I had to write this as an interval, it'd be that the mean is less than 52.8 and greater than 49.1. Now, that's our confidence interval, either one of these. So this is how I list your confidence interval on your quizzes as an interval, but is completely equivalent to the other one. Okay. Now I want to just touch on the meaning. Okay. So the meaning of this confidence interval, it's tempted to say that 90% of the time the mean is between 49.1 and 52.8, but that's not quite technically correct. So the meaning of this confidence interval, and I'll type this in the chat. Okay. Common mistake So that would be the common mistake. And let me just say why. So the population mean is not random. It is a fixed but unknown number. What is random is the sample mean and sample standard deviation, which dictates the length, dictates the so just as the reasoning behind that is that what's random is the sample mean, because every time you take a different sample, you're going to get a different mean, and the sample standard deviation, which likewise, every time you take a different sample, you're going to get a different mean, a different sample standard deviation. Okay, so the interval itself is random, not the actual mean. Okay. So let's work one more of these, and then I think you might also be interested in doing one where you use the other formula. Okay, so just as a heads up here, let us do, let's look at our quiz actually. And so like on your quiz that you'll have, I mean, preview it. Let's look at question 14. Okay. And let's work this problem. So the first question is which formula? 1 or 2? Okay. Then I'll go back to sharing my iPad and we'll work out this value. So what do you all think? Which formula is it? Okay. Well, maybe, okay. Excellent. So Shelby is 100% right. It's the first one, and she's saying that that is because we have the sample standard deviation, and it's given to us as 1/2. So S is 1/2. What else do we know? Like if I asked you to name the variables. Well, I think the average resistance is going to be very important. It's going to be 5 ohms. We also know that we have a sample size N of 30, and we have a 90% confidence interval. So that tells us that our T with 29 degrees of freedom with alpha over 2 is going to be 1.699, the same as before, right? So we have that 1.699. And I think that's everything we need to know. So in order to calculate this confidence interval, I'm going to do x bar plus or minus t of 29 degrees of freedom of alpha over 2 times s over root n. And we're just going to plug in this information. So I'm going to have 5 plus or minus 1.699 times s, which is 0.5. So I'll make that a times, and that's a 0.5, divided by root 30. And we need to determine the plus and the minus of this. And then we found our confidence interval. So it's not too bad, right, to find confidence intervals. And we're going to get that the mean resistance is between 4.84 to being as large as 5.15. So 90% of the time, the population mean will be a number between 4.84 and 5.15. Okay. So this is our 90% confidence interval. And let's try one more problem. And I want to okay. I took this from your review, actually. Okay. So first question is, I want you to name the variables, and I want you to tell me which formula we should use. Okay, so let's name our variables. So like there's a sample average. Yeah, so we want our sigma is from the population. And we're told that our sigma is 1.8 pounds. We have an N of 36, and the sample mean is going to be 5.4 pounds. Okay, so what we have to do here is we have to calculate x bar plus or minus z of alpha over 2. And by the way, we want a 90% confidence interval. So that tells us that alpha is 10%. Okay. And we're going to take this z of alpha over 2 times sigma over root n. Okay. So we know a lot of this. That's 5.4, and that should be plus or minus this z of alpha over 2, and this comes from a calculator. But it comes from a different calculator with the z distribution or normal distribution. Okay, so we're going to use this sigma, and it's going to be 1.8 divided by root of 36, and we have to determine this value of z. So let me show you how you do that on your online calculator. So under the calculator section, you need to go to the inverse normal distribution right here, okay? And under the area, you want to put alpha over 2. Alpha over 2 is 5%, so it'd be 0.05. Because we're using a z-score, it's always going to be mean 0, standard deviation 1. Okay. And I would recommend putting the above. And it's going to tell you that to the above is going to be 1.645. So that's our value of Z alpha over 2, is this 1.645. Okay, if you did below, you get the same number, but it'd be negative. So it doesn't really matter if you do above or below, but I would suggest to do the above. Okay. Okay, so now let's go back to the iPad and finish off this problem. So when you plug in all this information, your confidence interval should look like this right here. Then you just need to calculate it out and determine what the upper and lower values are. Okay. And you're going to get 5.89 is the upper number, and the lower number is 4.9. Okay, 4.90. Okay. And that's your confidence interval. Now we have one more thing to talk about. Okay. And what we have to talk about is a confidence interval for the difference in means. Okay. Now, before I get to that, I wanted to do one example in R of just calculating a confidence interval in R. Okay. So here's going to be a data set that lives in your library, Sleuth 3. Okay. Okay. And the data set that we're interested in, case 0202. Okay. And so you're probably wondering, what is this data set about? And what this data set is about, it's about abnormalities in schizophrenia. Okay. And this data set investigates psychological indicators associated with schizophrenia, and they studied the socioeconomic differences by examining 15 pairs of monozygotic twins. And one of the twins was schizophrenic and the other was not. Okay. So one thing that we're going to do here is that we're going to take the difference. And the difference here, I'm going to take it, I have the unaffected twins' brain size. So what's recorded is the unaffected, the volume of the left hippocampus in cubic centimeters, and the volume of unaffected versus affected. And what I want to do is I want to see, so here's going to be the question. If you're a medical doctor, what you're interested in is, are the brain sizes, that is the left hippocampus, for unaffected or non-schizophrenic individuals larger than those who are. Okay. So the difference here is going to help us measure that, because what I'll have is I'll have a data set that reflects the difference between these two individuals. Okay, and it's not just any difference of a randomly chosen individual. These two are very specific differences. Okay, so I'm going to take the difference of the non-schizophrenic unaffected versus those that are affected. Okay, now let me ask you, why is this difference useful? Well, it'll answer this question, right? If the brain sizes for non-schizophrenic are larger, then larger in general, not for every specific individual, then for non-schizophrenic, then I expect this difference to be greater than 0. Okay, so it indicates non-schizophrenics have a larger brain size. Okay, and this would be important if you're a doctor, because like it would be a way to try and determine if an individual is schizophrenic or not by measuring their brain sizes. Okay. One thing I want to say is that when I take this difference, I have controlled for the socioeconomic status and a lot of confounding factors because they are twins. They're raised in the same environment. They have the same geographic location. Their parents have the same economic status. So this unaffected versus affected, taking the difference, this is what's called a matched pair experiment. And it's one of the most powerful sampling methods that are available in statistics. Okay, so the data is really deemed to be very reliable. Okay, because we have an identical twin, which is hard to come by. So one thing that you might talk about is generally in this data set, you need to satisfy the central limit theorem. So that is, I need to know, is my data independent? Is it identically distributed? And the answer is yes, it is identically distributed. Because it is measuring a difference, and we have no reason to believe that the schizophrenia would be different across individuals. Okay, now the independence, this comes because we're subtracting out and we're taking the differences between these two individuals. Okay, and it's not likely that the difference of one twin is going to affect the difference for another twin when that other twin is somewhere across, located in a different geographic location. So independence is a fair thing to assume here. Okay. So now on to this confidence interval. So the command is Ttest, and this is a command that we'll return to. And I'm just going to do it on the difference. So you feed in your data. Now, there are other arguments that you can feed in. So I'm going to do a 95% confidence interval because that's the default. But we can change that So when I just run this command right here, is going to give me the confidence interval right here. That's the 95% confidence interval. If I wanted to try and change this, I can look at the documentation for the t-test, okay? And I can affect the confidence level here. So if I want to specify a specific confidence level, I could do like 0.99. Okay. Then I should be able, and then I can access that confidence interval just by asking for it right here. So that's the conf.int. So this would be the syntax. You feed in your data, you feed in your significance level or your confidence level, then I can read in, I can just get that piece of information for the confidence interval with this $conf.int. And here's my confidence interval. It's 0.015 to 0.38. Okay. If I wanted a 90% confidence interval, it'd be a 0.9. And notice that I get a different confidence interval right here. In particular, this is a smaller confidence interval than this one with a larger amount of confidence. Okay. So I'm going to ask you two questions. The first is, what does this confidence interval say? Well, it says we believe that the mean difference for non-schizophrenic versus schizophrenic individuals is positive. Because the confidence interval does not contain any negative numbers. Hence, on average, we would expect a difference between, and it depends what confidence interval you go with. If you go with the 99% confidence interval, we would expect it to be between 0.0155 and 0.38 cubic centimeters larger. So it's saying that there is a difference between schizophrenic and non-schizophrenic brain sizes. Okay, and the confidence interval was able to answer this question affirmatively for us, which would be a very important thing for a doctor. Here's my other question for you all. Question: why are larger confidence levels associated with a larger interval? So for example, the 99% confidence interval is And what's your answer for that? How about this possible explanation? So let's consider this. Let's say there's a 60% probability someone is between 5'11" and 6'3". Okay, and that probability is probably an overestimate. Okay, but I could be 100% sure someone's height is between 1 foot tall and 10 feet tall. So here I'm more confident, there's a higher probability, but look at the interval. The interval has expanded and includes more possible outcomes. So of course, everyone is between 1 foot and 10 feet tall, and I've made a very safe statement there. But what's harder to say is that someone is between 5'11" and 6'3". Okay. So that's a smaller interval and a smaller probability. So that's all there is to it. So that's all I have for today. And next time we will cover confidence intervals or differences between two populations. Okay, so we have one topic to cover before your exam, and that's all I need to do. So I'll talk to you all on Friday, and feel free to get started on your review. Okay, I am hoping that your chance to discuss the review with me is on Monday. So I'm hoping everyone goes over that review. You can take the review as many times as you want and your highest score is recorded. Okay, so there's no reason not to take it, even if you don't get a great score. Okay, all right, I'll let you all go and I hope you have a good one. I'll see you later. Thanks.